Welcome to lecture 45. In this lecture, we will continue our discussion of gravitational waves that we started in lecture 44. Recall that in lecture 44, we discussed gravitational waves in vacuum. This, in turn, lets us discuss the propagation of gravitational waves in empty space. In this lecture, we want to include matter in the Einstein equations, which will let us discuss the generation of gravitational waves. To get started, consider again the Einstein equations without cosmological constant, but this time including the possibility of matter on the right-hand side. Let us again take the weak field limit, meaning that we want to approximate the full metric field as Minkowski space, which is just the diagonal matrix with constant elements, and a small fluctuation h around this Minkowski spacetime that is assumed to be of very small magnitude compared to the Minkowski spacetime background. Following exactly the same steps as in lecture 44 and using the same gauge fixing conditions as in lecture 44, we find that we can write the Einstein equations in the linear regime in terms of a wave equation, which is given here in equation 45.3. Whereas a reminder h bar here was this combination of the original metric field fluctuation and the trace. So this wave equation here is such that we get back the results from the previous lecture if we neglect the energy momentum tensor term here on the right hand side. So if there's no matter, there's no energy momentum tensor, or the energy momentum tensor is 0, and we get back the wave equation that we solved in the last lecture. However, in general, the energy momentum tensor is non-zero, and as such, then the wave equation here is inhomogeneous. There's a non-vanishing term on the right-hand side, and it corresponds to a wave equation with a source. We know how to solve such equations. There's the Green's function methods that is central to discussion of classical electrodynamics. And we're going to use this technique to solve the inhomogeneous wave equation for gravitational waves. How does this work? Well, we define the Green's function g to be a solution of an equation that is just like the wave equation with a delta-like source on the right-hand side. If the solution g to this equation here is known, then we can write down the solution to the inhomogeneous wave equation on the previous slide as follows. Then h bar is equal to minus 16 pi g times the integral over spacetime times this function g times the source term. We can easily prove this by acting with the box operator on both sides of equation 45.6. Then on the left-hand side, we have box h bar, and the right-hand side, because the box is acting on the coordinate x, we can pull it through the integral over y, and then the differential operator acts on g. Now we can use the defining equation for g over here to replace the box on g inside the integral. We find that it's equal to a delta function, and then we can use the delta function to do the integral over y to find the wave equation that we were trying to solve. So this is why equation 45.12 is a solution to the inhomogeneous wave equation. There are several different functions g that fulfill this second order differential equation. As with most physics problems, we want to take a physical solution, which in this case corresponds to the retarded Green's function, or equivalently to the Green's function solving this equation with retarded boundary conditions. The function here is given in equation 45.15, and the proof of this is left as a homework problem. Once we have this specific form of the Green's function, we can plug it into our solution and find that the gravitational wave strain rate h r is given as an integral over this complicated function here, which we'll simplify in the following slides. So first note that, go back here, that there's a delta function here that we can use to do one of the integrals. In particular, this is a 4-dimensional integral that includes an integration over y0, and we can use this delta function to do that y0 integral in a straightforward manner. So doing that, we find that the strain h is given as an integral over just space d3y of this energy momentum tensor with essentially a retardation effect. This is an arbitrary solution, meaning it's a general solution for arbitrary source for the strain rate h. However, we can still simplify the results further if we use or if you assume specific sources T mu, such as in particular localized sources. Before we do so, however, let's just rewrite the solution again by just converting our generic results from the time domain to the frequency domain. And to do so, we just do a Fourier transformation of our result h into a function that depends on frequency omega instead of time. If you plug this into the generic solution from the last slide, what we get is that the strain rate here is given as an integral over the space and the time domain, and includes this Fourier transformation factor. Now we can further simplify this result by also converting the energy momentum tensor to Fourier space, then sort of brings in this Fourier transformed energy momentum tensor and its Fourier factor. And then we recognize that there's an integral over x0 where the dependence is just in this exponential here and that exponential there. So we can do the x0 integral, and the x0 integral, because these are just exponentials, bring us down a delta function, omega minus omega prime, which we can use in turn to do the omega prime integral. Long story short, we find that in frequency space, the Fourier transformed strain is given as an integral over space times the energy momentum tensor in Fourier space and this Fourier factor. Now, this result simplifies further if, in particular, the source is localized. So if we have a source, an energy momentum tensor that is basically only non-zero in an interval that is small. So for instance, the delta function would be one particular case, but it doesn't have to be delta function. It can also be a very quickly falling function. Then far away from this source, we can approximate this integral expression and get a compact formula for the strain rate. In particular, if the source is localized, then we can assume that y here is always much smaller than x if the source is far away. So we can approximate the difference between x, where we measure the gravitational wave, and y, where the gravitational wave is localized, to be just approximately equal to x. And we denote the absolute value of x as r. So if we do this, then we find that for the localized source, the strain rate h is just given as 4 pi g e to the I omega r divided by r, and an integral here that does no longer depend on the distance r from the source. If you look at this form here, the radial dependence clearly indicates that in this case, the gravitational wave is just a spherical wave. We are almost done, except that we still can simplify the result further by remembering that we have, or that we can do a gauge fixing on the metric field fluctuation. So if we use again the same gauge fixing condition as in the past lecture 44, we find that we can use the divergence of h mu to be 0. And in frequency, in frequency space, this implies that all the elements of the strain that have a 0 somewhere, so the first column and the first row of the h mu strain tensor, are uniquely fixed by the divergence of the spatial components. Or other way around, the spatial components can be the independent components, and then all the time-lag components are fixed by the spatial components. Now that we have, in addition to the gravitational field, also matter, recall that there's a similar looking condition for the energy momentum tensor. This is not a gauge condition. This is just a statement saying that energy momentum are conserved. We can also convert this to frequency space, and we find again that the spatial components can be expressed in terms of the time or frequency components or the other way around. So not all of them are independent. In particular, we can use the conservation law of the energy momentum tensor to express all the spatial components, particularly the fully spatial components, or the divergence of the fully spatial components, in terms of these components of the energy momentum tensor, and the divergence of these components in terms of the 0,0 component of the energy momentum tensor. Keeping that in mind, we just going back to our result for the strain rate here. So we know that only the spatial components here are independent, which bring in only the spatial components of the energy momentum tensor on the right-hand side here. So we have an integral over only the spatial components of t, so integral by tij. So that's the object we want to have, and we can rewrite this in terms of the following combination, which looks kind of a strange combination to choose it, but its purpose will become clear in a moment. So here in brackets, I've written down the derivative with respect to xk of yi tij minus yi, the derivative of just tkj. And you can quickly sort of use the chain rule to verify that this indeed gives back our original tensor tij. However, if we look at this expression here, we note that if the volume here is infinite, then this first term here is just a surface term, which has to go to 0 for a physical source. So the first term here basically just vanishes, and we find that the spatial integral of tij is just minus the volume integral of yi dk tkj. Again, using the fact that the spatial components are not independent, we can use this relation up here to replace dk tkj in terms of the I0 component of the energy momentum tensor, which we have done here. And I will just note that because we're using modestly plus metric convention, pulling the spatial indices up and down doesn't change the sign of any of the expressions, which is why you see that the spatial indices are sometimes up and sometimes down here, because it does not make a difference. Okay, so now that we have rewritten this integral here once, we can collect the terms we have found so far, and we find for the strain rate for a localized source the following expression, which is now written in terms of an integral over weight yi, coordinate yi, times the 0j component of the energy momentum. It turns out that we can use the fact that the metric field is symmetric, so that means the strain has to be symmetric too, to rewrite this right-hand side and symmetrize it. So just writing yi t0j as 1/2 yi t0j plus the other way around yj t0i. And if we do that, then we can use the same trick as we've done in writing the integral over tij again. So we can write this integral here as a chain rule that involves a total derivative. And we can use the fact that the total derivative gives just a surface term to rewrite this combination here as integral over yi yj times the gradient or the divergence of the 0k component of the energy momentum tensor. Then again, using the fact that these components are not independent, we can relate the divergence of 0j in terms of the 0,0 component of the energy momentum tensor, and we find that this integral here just gives us an integral that involves two coordinates, yi and yj, times the 0,0 component of the energy momentum tensor. Now, it turns out that this integral here is a well-known thing. It is just the quadrupole moment of the energy density. If 0,0 component of the energy momentum tensor can be sort of interpreted as such. And then this formula here can be written as the I times the frequency over 2 times the quadrupole moment of the energy momentum tensor. Collecting again all the terms, we find a very compact formula for the strain rate in frequency space. It's just given as minus 2g times the frequency squared, spherical wave factor times the quadrupole moment of the energy momentum tensor. This quadrupole moment of the energy momentum tensor is not dependent on the distance of the source. It's an exclusive property of the source itself. It depends just on how the energy of the source is distributed, and the sort of spatial dependence in terms of the distance from the source is exclusively captured by this spherical wave factor. Of course, this is the expression in frequency space. We can as well convert this expression back to the time domain by just doing the inverse Fourier transform of this relation here. So then on the left-hand side, we get the strain rate factor as a function of time. And on the right-hand side, we have that the frequency omega is the same, or converts to time derivatives. So we find that the strain is proportional to the second time derivative of the quadrupole moment in the time domain, where there's this retardation condition that says that we have to evaluate the time signal from the quadrupole moment in terms of this retarded time. Now, 45.33 is a very compact formula, and it lets us calculate the strain rate of a gravitational wave far away from our observation simply by knowing the quadrupole moment as a function of time from this source. And we will use that to calculate, in particular, the gravitational wave strain rate for a black hole merger from basically knowing the quadrupole moment of this system.